Dane started surveying in 2005, and once he started, he knew he was a surveyor at heart. He loved the ability to be outside and perform historical research, perform mathematical computations such as tonight, meet with landowners, cut line, investigate and assist in legal matters, and learned new equipment and technology. Dane received his land surveying and training certificate in 2007, subsequently became a professional land surveyor in Maine in 2009. Dane is currently licensed not only in Maine, but also Vermont, Texas, Colorado, and Oregon. You got any new ones since then, Dane?
No, no, I'm done for a while.
You're done
Just
for a while.
like paying for them.
I love it. In all, has gained over 15 years of experience, which now would be 19, going to be 20 next year. So you can see this bio is old. That's how long.
Yeah,
That's how long Dane's been on mentoring Mondays with us. I love this. Working different states and having different survey disciplines, including residential, commercial, ALTAs, engineering, transportation, and construction. Dane is currently works as a professional land surveyor at Colorado Department of Transportation. Dane has his passion for teaching, which is why he's put together the fundamentals book and why he is a staple for Mentoring Monday. So I will ad lib it as much as I can on that one. So as
yeah,
always, Dane, we love your time. We love your conversations and your presentations that you put together to help facilitate the FS exam and those coming up behind us in the next generation. So love it,
great.
Mr. Dane. Thank you, sir.
Yeah, thank you very much. Before we give them least squares, I've given a talk before on traverse adjustments and the compass rule. I'm not going to take too much of our time tonight, but if y'all want to screenshot this this shot or this screen right here, um, I really got to thinking about it, and I was teaching my group of guys the other day, and I added this slide to my presentation um, because it really is the essence of survey on this page. I
Mhm.
preach all the time. If you're going to go into this exam, knowing um, a few things, the things should be knowing right triangles backwards and forwards, knowing how to use sine, cosine, tangent, knowing what that means, knowing the Pythagorean theorem. And then number two is truly utilizing and understanding ratios or proportions of things. And we're going to see that, you're going to see that over and over and over. Um, Double, single proportioning, horizontal curves. That's all horizontal curves are right triangles. That's it. Proportioning comes into play whenever you're doing the degree of curve versus um, your intersecting angle, all that kind of stuff. That's all proportions. But when it comes to traverse adjustment, this is a perfect example of right triangles and proportionality all combining. And that's all a compass rule traverse adjustment is doing. It's just, you have your overall misclosure distance. You can break that down into a triangle, right triangle, that creates your latitudes and your departures. And you move that direction, the same direction that you were off at the end, you move that direction a certain amount of, a certain proportion based on the length of your leg of that traverse. So, yeah, I won't go into all the math of it, but I just want to leave it up to make sure y'all could screenshot it, maybe add it to your add it to my presentation that I gave on traverse adjustments.
And
Okay.
I just threw that in
Yeah.
the chat. Week 112 for those watching later, but week 112 was Travis Adjustments. So
All right. Perfect. Yeah. Um, I just revamped this, and I also just revamped my section 6 calculation talk as well. Um, I won't get into that one, but I did add because I got banged pretty hard up in sorry, I gave a talk in Washington at the conference up there. And the example I give for section 6, it's a section that's pretty square. Okay. And you got to figure out the west half of the west half and the north half of the north half. trying to get those government lots all generated and calculated. And that's all fine and dandy. And the way I showed you does work. However, what if your section is 3 miles long by 1 mile wide? And I know it sounds ridiculous, but I just broke one of these down up in Lynn County, Oregon, where the north half of the section was like 2 miles long, right? So if that happened to be section 6, then my math would not apply. You have to once again do a proportion on that west line and that north line to generate your distances for your government lots. Okay. In this case, the government lots would be something like that. Okay. All right. So
But before you jump in, Dane, I was just gonna say
yeah,
for those watching now, Dane has two presentations. One is the screen share that's showing, and then he has one that's an overhead camera that
yeah.
he draws on. And if you right click on that, you can say pin it, and then you can slide between the two screens that he's got going on there. So I do that on the recording side of it, but for those that are watching now, you'll have to kind of slide back and forth between the two cameras.
Okay. All right. All right, so let's get into least squares. Hopefully I don't have any brilliant mathematicians on tonight.
You got a few.
But okay. Feel free to chime in. This is geared for the FS exam, and the knowledge that you need for that. Okay. But the knowledge that you learn in this, you aren't going to go into this exam and they aren't going to say perform a least squares adjustment on these data points. Okay. They aren't going to do that, but they will ask you the concepts behind it, or they might provide you all the answers to a lot of it and you have to fill in the last part or something like that. Okay. So I don't want y'all thinking that you have to memorize these steps and go through and know exactly how to perform it. What I really want you to understand is just the overall idea behind what least squares, and we're going to be doing a linear least squares adjustment. Okay. So a little bit before that, when I first started doing this, my boss kept calling it a best fit line. And and to me, that makes sense in my brain. That makes sense. A best fit line. Okay. But a least squares, a best fit solution, is obtained when the sum of the squares of the residuals are minimized. The result reduces the amount of correction to the data set. So you want to come up with a solution that you have to adjust it minimally. Okay. You want to create a line amongst a data set that is going to create the least amount of havoc into that system. Okay. And I'll explain what this means. First off, what you got to figure out, what you really understand is what is a residual. So here's a target I'm drawing now. Here's your target. Okay. And we all know precision versus accuracy. Okay. So you're all set up with your rifle and you're shooting a target. Okay. And you shoot 5 rounds at that target. Let's say your rounds hit the target like this. Okay. That right there, that little cluster tells me something. That tells me that first off, you're shooting precisely. You're not accurate, but you are precise. The second thing this tells me is there is no well, let me get into this too. Random error. And what's the other one? I'm drawing a blank. You have random errors, you have blunders, and you have systematic. That's it. Okay. These are the types of errors. Blunder, that's the mistake. Okay. You pull your tape out and you measure 23 feet and you just read it wrong. It was supposed to be 22 feet. Okay, the tape was stretched out to 22. You wrote down 23. That's a mistake. That's a blunder. Systematic error. Systematic error is a good example of that is if you have the wrong prism constant and you're taking shots with your total station all day, and every single shot you saying the prism constant is negative 0.13, when in reality, the prism that you're using that day is negative 0.23. Okay. So every single shot you took is 0.1 tenth off. And that's pretty easy to fix. You can identify it. You know what you did and you can correct it. You can shorten the length of every single shot you took that day by 1/10, and your data set is going to be back to being correct. That's a systematic error. They're identifiable and fixable. Blunders are just that, a blunder. Then finally, you have random error. Random error, those are unidentifiable and they're not fixable. You can reduce them as best you can, but you will never eliminate random error. It will always be there no matter what you do. You can try your best. You can enter the right humidity into your data collector when you go out there to help with that. Wind can add certain errors. There's all these environmental type errors and random errors that can occur in the system. So when I take my rifle and I shoot 5 rounds into this target, what I'm seeing is there's very little random error associated with this system because I'm getting the same result almost every time. What I do see, though, is a systematic error. This looks to me like my scope is not well adjusted. If I can adjust my scope and move this cluster down this direction, the next time I take my 5 shots, it'll look something like that. Now, that is both precise and accurate. Okay? If I take shots and they look like this, that has random error. That's telling me wind is being accounted for. The nervousness of your trigger finger, your breathing, all kinds of things can add all this random error. And you're going to get non-precise and non-accurate in that case. Okay. Now, another way to identify random and systematic is, well, not define random and systematic. You can't identify random. Is the term residual. And all residual is, it's the delta or difference between what it should be and what it is. So it's should be versus is. Okay. These shots should be on the center of the target, but they're over here, here, all over here. Okay. It's pretty rare you're going to get perfectly in the center of the target. Well, the distance between what it should be and what it is, that distance right there, that essentially is your residual. Okay. The difference between, what do I have it here? A residual is the difference between predicted value, what it should be, to the observed value of any point, any data point in the set. So from what it is to what it should be, that's your residual. Okay. Now with least squares, the whole objective is to reduce that residual of each data point. Okay. That's what we're going to be doing, is reducing that residual. Sometimes you have to increase the residual on one point to decrease the residual on a bunch of other points, maybe. Okay, we'll get into that. A good example of residual, as I drew here, is your calculated position versus the pin that you find. Okay, so you have a deed in front of you, you deed plot it, and you produce some calc points based off aerial imagery, whatever you're working with. And you give those data calc points to your crew. They go out and they start recovering monumentation. and they're calling you back and saying, hey, we're finding pins within 1/10 of your calc points. Well, that tells me two things. One, you're not going to have to do a lot of boundary analysis on the back end because you're probably going to be holding those pins, right? And the other thing is your residuals are very small between what you're calcing and what you're actually finding. Okay. Does everyone understand that, what a residual is? If you have any questions, Clint, monitor the chats and let me know. All right.
Yep, you're good so far.
Okay. I know I learn personally through visuals. Okay. And I don't know where I saw this, but the second I saw it, this was pegged in my brain as a perfect example of what a linear least squares solution is all about. Okay. All right. Let me explain it. So, you know, those pegboards in your garage, right? That you hang your tools on. Imagine you had a pegboard. I'm drawing again, by the way. You had a pegboard. You have a pegboard, and you randomly hang from certain holes in your pegboard. You hang springs from those holes. Okay. You attach one end of the spring to the hole, and you attach the other end of that spring to a broomstick. All right. So you have your broom hanging from extended springs from the pegboard. Okay. And you grab that broom and you slide it up and down against that pegboard and you let it go. That broom eventually will come to a rest. Okay. It's not going to constantly be moving. If it does, you've invented a perpetual motion machine and you can go become a billionaire. Okay. Eventually that broom will come to a rest. And where that broom comes to a rest, it's going to find equilibrium between all the pulling and pushing forces of those springs attached to the broom. It's going to find a position where the least amount of resistance and pull and push is being exerted on that broom handle. And when it finds that point, it's going to stop moving. Okay. It might bounce around for a little while, then it's going to stop. Well, what that broom did was it performed in the physical world a linear least squares solution because it found the exact position of that broomstick where the least amount of resistance is being exerted by each one of those springs. If I take that broom and I move it slightly up or slightly down from either end, it's going to spring and boing right back to where it was prior. Okay. The only way it won't is if I move where that one of those springs is attached to the pegboard. If I move this spring here, then the broom might go slightly up, let's say. Okay. I don't really know, but that's the idea behind what we're doing. Well, the resistance on those springs, we're going to see here shortly that essentially is what we're trying to reduce. These are the residuals we're trying to reduce. All right. When I was doing research into this, trying to figure out how to illustrate it and stuff, there are two different methodologies. I do mine with a perpendicular line. I should have mentioned this at the very beginning. What we're going to attempt to do here is, imagine if you go out and you shoot in a fence line along two pieces of property that you're surveying. Okay. I know these fences are pretty far zigzagging. I just want to do it to illustrate what I'm doing here. But what we're going to have to do, these are fence posts that I've located. What we're attempting to do is to draw a line between these fence posts And among this cluster of fence posts, that is a best fit line. And it would look something, I don't know for sure, but it would look something like that. Okay. Now, I've actually done this in CAD. There's a least squares linear regression that you can run in your in CAD. And what it's doing is what I'm about to show you. But what I wanted to get to is the distances from those fence posts to the fence or to your best fit line. You can do it in a perpendicular manner, meaning from the best fit line down to your point data point, it creates a right angle. I've also seen someone go creating a vertical line, which may or may not be right at a right angle with your fence line, with your best fit line. Okay. What we're doing tonight, and both of these methods do seem to work. I've understood it from a perpendicular perspective, and someone can chime in because I haven't really found a definitive answer on why use one as opposed to another. I actually wrote down, let me read this. Maybe I'll put it in here. There are two ways to analyze the distance between the points and best fit line. Either perpendicular residual distances or vertical residual distances. The concept works either way, trying to minimize the residuals. We will be utilizing the perpendicular residual method, but it is claimed that the vertical residual method allows for easier solutions for Y values. Okay. I'm not going to get into what that means, but hold up. Let me go back. That was their claim to use vertical as opposed to perpendicular. What we're going to do tonight is perpendicular distances. So from our data point to our best fit line, we're going to assume that it's a perpendicular line creating a right angle with our best fit line. Okay. All right. So this is to me, this is the concept, kind of explained it just now with the broom, but this is essentially what we're trying to do here. So look at this line to the left, and I got my data points scattered out through that line. Okay. Each one of those distances, I should have twisted. These are vertical distances, what I just said we weren't going to do, but the idea remains the same. Okay. If I were to draw a square subtended off of the distance between my data point and the best fit line, whether it's vertical or perpendicular, I'm going to create a bunch of squares here. Okay. And all this square is, it's same length as it is width. And that distance from the point to my line is going to tell me how big of a square we're generating. Well, this line right here is the best fit line for this data set. I took that line and I drug it down a little bit. See the distance between this point and the line? Now look how close it is right here, if y'all can see my mouse. Okay. And if I go through and I figure out the area of all those squares and I add them up, it comes to 4.6639. I did the same thing on this line. I created all these squares based off of the distance from my data point to the line on each point, found the area. If you add up these areas, it comes to 5.083. Your true best fit line will create a line where the area of these squares is as small as you can get. I just took that line, I moved it slightly down a little bit, and it skewed my data to have a larger N area value. So if I take this line and I slightly move it up, just a fragment of a centimeter up on this end, it's going to generate different areas and when I add them up, it will be larger than 4.6639. This is the smallest I can get. And that's the idea. That's why they call it least squares, because you're trying to create the least squared accumulative value once you've generated those squares. So that line, it can only be in one position, just like the broom will stop in that one position when suspended off of those springs. Okay. So this is the concept behind it. And now I'm going to show you the math on how to do it. Okay. Just like all other survey math, we're not talking about difficult high physics and rocket science here. This is all just adding, subtracting, multiplying, and dividing. It's just knowing when to do it and staying organized as you do it. Okay. There's 5 steps that we're going to follow, and I'm going to go through each one of these steps in detail. But this is the concept here. And Trent, I'll give you this slideshow, by the way. Okay. All right. So let's go through the steps. The best way I can explain all this is through an example. Okay. A real simple example. So what we have here is just Cartesian XY coordinates that I've plotted out on this graph. All right. So we have these 5 points, 1, 2, 3, 4, 5, and I've plotted them out. The objective is to create a best fit line between and amongst these points. So imagine these are fence posts that your crew came back with. You download your CSV file from your tablet, and you have to generate a best fit line between and amongst those fence corners, or fence corners or posts. Okay. So for all the steps during least squares process, each individual point's X and Y value will be utilized. So we need to know the X and the Y value, AKA northing easting. So don't get that mixed up. X is easting, Y is northing. So these would be flipped. In this case, we're just doing Cartesian graph X, Y. Okay. So let's get into it. Step 1 was we need to organize our data, and we need to come up with specific values as generated from our northings and eastings or XY values. Okay. So I'm gonna write them all out. I'm drawing now. So 0.11, 0.23, 0.65, 0.88, 0.910. All right. So the first thing we do is we take our X values, which is going to be the first column, X, Y, and I'm going to square each one of my X values. Okay. So this will be my X squared column. So 1 squared is 1. 2 squared is 4. 6 squared is 36. 8 squared is 64. 9 squared is 81. Okay. The next column is X times Y. So I simply take the X, multiply it times my Y value. 1 times 1 is 1. 2 times 3 is 6. 6 times 5 is 30. 8 times 8 is 64. And 9 times 10 is 90. All right. So now I have 4 columns here, essentially. I have my X's, I have my Y's, I have my X squares, and the product of X and Y for each point. All right, that's step 1. Pretty easy. Step 2, we got to sum up or add up all these values. Just add them all up. So if I were to go and add up all my X's, 1 plus 2 plus 6 plus 8 plus 9, I get 26. 1 plus 3 plus 5 plus 8 plus 10 is 27. 1 plus 4 plus 36 plus 64 plus 81 is 186. And finally, 1 plus 6 plus 30 plus 64 plus 90 is 191. And these are what I'm after right here. Okay. Step 1, create your columns, generate your values. Step 2, add them all up. At the end of step 2, I have 4 number values. Okay. I'm going to show you why we're doing this. You don't have to just blindly do this. I'll show you why. And don't forget, if we're doing northings, eastings, you got to flip it and make sure that these X values are really eastings. Okay. All right. Step 3. So back up to these. Step 1, create your values. Step 2, add up those values. Step 3, we got to calculate the slope of the line. All right, because at the end of the day, we're creating a line. That's what we want to do. All right. And we need to figure out a few things about that line. The y-intercept of it, where it's crossing the y-axis, and the slope of it. If I can tell you on this Cartesian graph, I have a line with a slope of 1 and it crosses the y-axis at 3. So 1, 2, 3. I know the line crosses right here and it has a positive 1 slope. So it's going to look something like that. All right. If I just tell you the slope, that's good, but I won't know where to place it because that line could be placed here. It could be placed anywhere I want. If I tell you that I don't know the slope, but I know it crosses right here, well, that's good, but does the line look like that? That is an infinite amount of options. So you need to know both the y-intercept, where it crosses the y-axis, and you need to know what the slope of it is. And from these values that we've generated, we will be able to determine both of those. And that's what step 3 is. What is the slope of our line? Okay. So remember, slope is the change. Slope is change in y value divided by the change in x value. So slope is also known as grade, which is also known as m, but they all are delta y over delta x. Think about a step, stairs, okay? You have this is also delta y is also known as rise. Delta x is also known as run. So on a stair, you have a rise and a run. This is the rise, how much it goes up, and the run is how long the step is. Okay? Well, if my stairs go up 1 foot and the run is 3 feet, 1 foot, 3 feet, 1 foot, 3 feet, you're going to create a line, right? And all these are latitudes and departures. Just like I said in the beginning, everything is right triangles. So I have this line here, and I know this point value and I know this point value. Let's say this is 0.00 and this is it would be 3, 1. Okay. So now I have, if I zoom into this, this is what I'm dealing with. This is 0, 0. This is 3, 1. So from this, I can generate my latitude, which is my change in y. Yeah, this could be written as delta lat over delta rise, delta departure. My latitude is how much did it change from this point to this point purely in a north-south direction. So I know I'm only dealing with my y values. Well, it changed from this point to that point it went from 0 to 1 with my y values. So my latitude in this situation is 1. That's how much my y changed. My departure, how much did it change from this point to that point in a purely east-west direction? Well, now I'm dealing with my x values or my eastings. That would be, I went from 0 to 3. So in this case, it's 3. So now I have a right triangle. I know this leg and this leg. Now I can figure out through the Pythagorean theorem what my hypotenuse is. I can figure out any angle I want. I can do anything I want now that I've generated this, okay? Well, that's what this triangle is all about. But what we're talking about here is slope. So how much did it change from this point all the way up to this point? Well, I would just simply do my change in y, which is my latitude, which is delta y, divided by the change in x, which is my x value, my departure, and I would get rise over run. So in this case, I have a 1 to 3. 1 divided by 3 is 0.33333. Okay, so my slope for this line is 0.3333. It's also positive. Just look at it like you're reading. If the line's going up as you read, then it's positive slope. If the line's going down as you read, it's going to be negative slope. And you can figure that out just by the math, because if I go from this point, which is 0, 0, to this point, which is -1, -1, no, be 1, -1, from here to here, well, delta y is 0 minus -1, 0 minus -1, over my delta x, which is 0 minus 1. Well, that would be 1 over -1, which would give me a -1 slope for this line right here. And sure enough, it's going down as you read from left to right, okay? So that's what slope is. Now, the formula looks a little bit more complicated when you're dealing with what we have here, okay? And I had a hard time trying to decipher what this is actually doing. And what it actually is doing, well, before I show you, the idea behind this is we're generating the slope of our line. And the way that it does it is you incorporate those values that we found in step 2, the 26, 27, 186, 191, okay? And you just plug them right in. N represents the number of points in your data set times the sum of your product of x times y, which was 191, minus the product of the sum of your x values times the sum of your y values, which is 26 and 27. And then the bottom is your number of points times the sum of your x squared values minus, this got me a little bit, but it's minus the sum. It's not x squared, it's the sum of your x values squared. So it's not 186, it's 26, okay? So let me show you what this actually is doing. The way it works is it's using area. That's what all this multiplication and addition in steps 1 and 2 is actually doing. It's creating those squares that I showed you right here, okay? And it's generating a slope based off of the areas of those squares. And it does work, I checked it. So the green square is my X times Y product. The blue square is my X and my Y product. So that if you see these circles here, they represent what I found up above. And sure enough, if I multiply out my values, my areas based off of those values, it does work. The key here is though, you're really looking at the area of difference between your green square and your blue square. That's really what you're looking at. So if I were to overlay my blue square on top of my green square, this area right here, this backwards upside down L, that's really the value that I'm trying to find here, okay? And sure enough, if you do it, if I get the area of my product square minus the area of the X and the Y summed squares, I get 253 square feet. The same thing is going to happen on the bottom. I generate my two squares based off of my areas, and the difference between them is what I'm left. And if I take the area on top of the division and divide it by the bottom, I get a slope of 0.996, which is almost a +1 slope, which is a 45-degree angle. Not quite, but very close, okay? Again, you don't have to memorize this. I just wanted to show you that it does work, and that's what this complicated equation is doing. It's generating areas, and the differences of those area squares is what is creating our slope calculation, okay? If you don't want to know that, just follow this equation. It's going to generate your M value, and now you have the direction of your line. You just don't know where to place it. And that's what step 4 is placing that line, okay? So everyone knows the y-intercept formula is B. B is y-intercept. B equals y minus mx. Okay. Again, we have to complicate it because we're dealing with coordinates as opposed to points. I'm sorry, coordinates as opposed to just a simple value. So if we plug in our numbers, the sum of our y value, which was 27, minus the slope we just figured out from step 3, times the sum of our x values, which is 27 was y, 26 is x, and I divide all that by the number of observations or points in our data set, which was 5, I get a B value. My y-intercept is 0.220. That tells me that I have a line that has a +1, nearly +1 slope. This was 1, 2, 3, 4, 5. And it's going to intersect my y-axis at 0.222, which is somewhere right here. And it's going to have a +1, so almost a 45-degree line, and it's going to look just like that. Okay? So I have all my data from all the points that I had at the beginning of this thing. I created a line that is perfectly best fit amongst and between those points. Okay? So I've defined my line, but it's pretty hard to, if I told you, hey, plot out, or hey, draw a 0.996, +0.996 sloped line intersecting the y-axis at 0.220, you'd have a hard time doing that, right? So what step 5 is all about is actually creating points on this line that you can plot out and then connect the dots for your line. Okay. And that's what step 5 is. It's pretty simple. Insert values into the slope intercept equation, y equals mx plus b, and you're going to get certain values. This is kind of an easy part because you can plug in whatever the heck you want into that equation, and it's going to start spitting out points that you can then plot out. And those points are going to plot out your best fit line. So the equation utilized is y equals mx plus b. We know our b value. We already figured that out in step 4, 0.220. And we already know our slope value is 996.996. Now we just got to plug in our x's and our y's. You can plug in any number you want for y and solve for x, or vice versa. Any number you want for x and then solve for y. Let's start plugging in numbers for x. I know it's going to be y equals 0.996. I can do anything I want. I could do 1,422.7321 if I want. I'll make it simple and just do 1 plus b value, y-intercept 0.220. If I solve for y with this equation, y will equal, what did I have? 1.216. So if x equals 1, y will equal 1.216. So there's one point I can use. By the way, I already have another point. Just by figuring out the y-intercept, where the line crosses the y-axis, I automatically have a point. Because I know a line on the y-axis is going to have a 0x value. And I know the y value at that position will be the y-intercept, which was 0.220. So I have 2 points already. Let's say I want to do another point way over here, so I can just draw a straight line between them. Let's say 10. So y equals mx plus b. Y equals 996 times 10 plus 0.220. I didn't figure this one out, so let me do it. 0.996 times 10. I'm doing PEMDAS, remember. Be 9.96 plus 0.22. Y equals 10.18. Okay? And this is making, so if I have an x value of 10, I have a y value of 10.18. Again, I can do whatever I want. I could have plugged in 5 for my y and solved for x if I wanted. And this is making sense. With a slope of almost 1-to-1 or 45-degree angle, that means that my x's and my y's will almost equal every time. And sure enough, they are. When x is 0, y is 0.22. When y is 1, x is 1, y equals 1.216. When x is 10, y equals 10.18. See that? They're almost the same every time. If I would have had a different sloped line, these values wouldn't be so pretty and neat. Okay. So what I'm getting at here in our step 5 is just generate a few points that you can now draw, put a straight edge or whatever down, and generate a line going through those points. That line that you draw with that straight edge is going to fall right between all your data set points, because that line was generated using those points and minimizing the residuals from each data point perpendicular to that line. And again, the way we did it was the use of areas and the differences of areas amongst all these little squares that we generated. Looks something like that, okay? And the end result of that line, if I were to add up the area of all these squares, I'm going to get a value that is the smallest value possible that you will ever see. If I draw that line slightly different amongst those points, that value will increase. Yeah, I may have decreased some of these squares, the areas of some of them, but I guarantee I increased other squares more than I decreased the others, the smaller squares. Everyone understand that? So that's the idea behind it. So the end result is I have this line that I've generated that reduced the perpendicular residual value from each data point to that line. And again, there's only one place on planet Earth that that line can be laid if it was a fence line, okay? So yeah, I just had a comment here. This is a good way to reduce your legal description from 105 calls from fence corner to fence corner, going down your line, and just creating it, just doing it 10, right? It all depends on the deed too. You don't know what that deed is calling for. Does it call for the fence? Is the intent to be on the fence the entire time? Or is the intent to go from something like this? So we have a monument here and a monument here. And we have a fence that's doing this. Okay. Is the intent to go along the fence? Or is the intent to go from monument to monument? I know it sounds silly, but maybe the intent was to go along the fence. Then you don't have to do what we just did, right? But that's a whole nother legal matter. I just wanted to throw that out there. So I do have a little bit of time for questions, and we can go into that traverse adjustment slide that I showed, Trent.
Yeah.
Or I
Shorter's got his hand up, so he's got some stuff
okay.
to chime in on.
Yeah,
So.
good.
Yeah, thanks for your presentation. So maybe not everybody was there, but I've been using least squares for 50 years. And mainframes, I've never applied it to trying to figure out a best fit of a fence line. Mostly, you know, an array of points from a survey. The
You're
biggest
talking like, you're talking like you take 6 shots trying to locate a monument, let's say, and generating a value for that monument. Is that kind of
Well, originally, like, you know, triangulation networks, where you had, you know, angles and distance measures. And then once you got GNSS, maybe you're mixing, you know, terrestrial observations. And the big power of least squares is actually a weighted least squares,
yeah.
because the standard errors for what you're using to measure, whether it's a steel tape, a 15-second instrument, a 1-second instrument, a GNSS of different points, is getting the weighting of things like centering errors and standard errors for the measurements. And I see a lot of people when they start using least squares kind of ignore the importance of having the correct weightings on those observations, and they get a statistical result from an adjustment like a chi-square test, and you know it doesn't fit, so that they put a general scalar number and you can look at the adjustment results, and if their scalar number is way out of whack of 1, you know, it's a weighting problem that they have. And so the other thing I'd like to share as far as a practitioner of a really good way, a tool for using a least squares adjustment, say something like Starlink, that you have is, we've all worked with plats that have multiple errors in them. You know, we got a dirty plat, it'll drive you crazy if you're trying to do Kogo comps and, you know, lots don't close, boundary doesn't close. I ran into several of those, and I just put in the observations of the plat, even before going to the field, put in the bearings and distances from the plat. As that adjustment, then, as you said in the beginning, it makes a best fit. Boom, there's a distance that's off by a foot or 10 foot, or here's a bearing that's got the quadrants flipped. It can save you so much time when you have you know, a very air prone plat that has multiple problems
Yeah.
with it. Yeah. So
Yeah.
that's all I wanted to share. I'm sure you have others, but thank you for your presentation.
Yeah. Thank you very much. I'm glad you were here. I am guilty of what you mentioned, before, just massaging the data and not weighting things as I should, assuming my VRS RTK shot is just as good as uh a chained in point done in 1829, So it well, I'm not that ridiculous, but you get what I'm saying. Like you do forget the importance of that, Like, was one of these fence posts that we've been talking about, was it, all these other fence posts are just out in pure sunshine, no obstructions, but this one you had a bad fix on. It was plus or minus 5 feet, let's say, because you're under a giant oak tree. Okay. Well, do you really want to do you want to weight that point the same amount as these other clean shots? No, you probably don't. You'd either throw that one out. Well, if it's really 5 feet, then you definitely throw it out. But what if it was, 3/10? Would
Yeah.
you shouldn't be incorporating that point into your data set if it's going to add error to all these other points. Because at the end of the day, what you're trying to do is generate that nice clean line with equally observed data. And if it's not equally observed, then you need to weight it accordingly, right? So yeah, just keep that in mind.
Another example that ran into, so say you have 8 tribracs out on the project, multiple receivers or instruments, and you didn't check the calibration of your tribracs before you started, but one of them was out of whack. So
Right.
you knew where that went. So you open up the weighting of that one instead of having a 1/100th of a foot centering error. You make it
Yeah.
a 1/10 of a foot or whatever you saw in the calibration. Then suddenly that adjustment all comes in because
Yeah.
it's systematic error on one piece of equipment.
Yeah. Yeah. Good. Systematic. It was identifiable. It was uncalibrated, and you know how much to fix it now. So that's a great example. Anyone else, Trent?
Nobody's got their hand up, but anybody can definitely unmute if you got
Okay.
questions, need more clarification. There's a lot when we do these math heavy ones.
Yeah.
It's definitely a
Yeah.
lot of radio silence. I think people digest it later, or come back and watch
Yeah.
it later too. But yeah, these ones are the math heavy ones are always kind of a quiet
Right.
session.
That's all right.
Yeah, no, exactly.
Yeah. Let me go over this section 6 then. If no one's got questions, if y'all do, you can pull me back into it. But
Cool.
so I have this whole presentation on, section 6 calculation, and really you're shoving all that error into the north half of the north half and the west half of the west half of section 6. All this white area in here should be your 60 chain by 60 chain square. All that extra, as they call it in Louisiana, they call it lanyap. But all that lanyap, all that extra, whether it's excess or deficiency, is going to be shoved into this red hatched area. Okay. And if you have a situation like this, where your section is relatively square and close to being regular, your 80 chain by your 80 chain, right? Then just simple averaging will work to generate the values of all these question marks here. But what if you have a situation like this, just like I showed at the beginning, where you have this elongated section, okay? Well, what you have to do there is your averaging will not work, because if you average out the north line and the south line of this west half to the west half, when you do that, you're going to create a midway averaged line there. That length is what you're going to get, and that's not what you want. You want to be way down here, along the 40 along 40 feet up from your south line. I'm sorry, 40 chains up from your south line. So how do you do that? Well, just like everything else, it's going to be proportioning. Okay, I have the fancy formula here if you guys want to take a screenshot of this. But what it's basically doing is this right here. This is the idea of it. If I go 20% of the distance up that west line right here, then I'm going to need to figure out what 20% of the overall difference between my north line and my south line is. So if the overall distance between my north line and my south line is 10 feet, let's say, well, then 20%, if I go 20% up that line, then I'm only going to be taking 20% of that difference, which would be 2 feet. If I go 70% of the way up that line, I'm going to be generating 70% of that 10 feet, which would be 7 feet right there. Okay. And I can generate whatever distance I want. I just chose 20 and 70, but when we're doing this for real, we need to work with chains. So I'm going to generate what's the percent of the line that I'm going to be going up if I only go 20 chains on a 328.33 chain line. Well, I'm only going to be going, what is it? Let me see, 20. Oh yeah, it's this one. It'd be 20 chains. It'd be 6.1%. So 6.1%, I'm going to go 6.1% of the way up that line. Well, if that's all I'm doing, I'm only going to be able to utilize 6.1% of the difference of this line down here and this line right here, which I calculated to be 1.12. So 6.1% of 0.12 is only 7 thousandths of a foot. Okay. And these distances are all made up. I just did them to express what we're trying to do here. But so it's all about proportionality is what I'm getting at. Okay. If you have a section that looks like something like this, where it's nice and squared off, simple averaging will get you close enough for what we're doing. But the second you start having a really skewed irregular section for section 6, that's when you're going to have to start doing those proportions. Okay. I just want to throw that out there as a caveat to my presentation on this, Trent.
Yeah,
I don't know.
That was good.
Yeah. Okay. Yeah, and that's really all I have. If anyone has any questions about anything, let me know. If anyone's in Colorado, I'm going to be speaking at the Colorado makeup conference. So I was deathly sick during the conference. So I promised them I would do a makeup session, and I'm doing it this Friday at Denver Water downtown. I don't know if anyone's in Denver on this call, but I just want to let y'all know. Contact me and I can give you all the details.
Yeah, that'd be awesome. I know you got sick just a day or two before that conference. That was crazy.
Oh man, yeah. I
Yeah.
waited to the last minute hoping I'd get better, and I never did. So I just promised them that I would I would make it up to them. That's what I'm doing now.
That's awesome. I love it.
Yep.
Anybody get cut? Any questions? Specific questions? Anybody still there?
Yeah.
I love it. We are back again next week. So the next two Mentoring Monday sessions are one's about surveyors and QuickBooks, and then another one is another project management software out of Florida. They reached out a couple of weeks ago, and we had a spot for them. So that goes in line with like the Q factors and the compass and a couple of the psionic automations and stuff that we've done. So those ones are always good stuff. So anything to help on the project management side. And then wisdom is again this week, still finishing up chapter 11. So we're going to try to wrap up that book. But on a side note, we're hoping the next book for wisdom Wednesdays starting in September will be The Pincushion by Lucas. I've been chatting with him about making sure that we can do that. So far, tentatively, it looks like we should be good to do that in September. So that'll be another fun one. But so if nobody's got anything, we will let Mr. Dane get some dinner. All right, guys. Have a good week. We'll chat with everybody on Wednesday. If not, we'll talk next week. Did I lose everybody? Where'd we go? All right, bye, guys.